All right, so we're going to get started with the second talk in the session. This is a distinguished paper. Neta Elad will give the talk on an infinite needle in a finite haystack.
Thank you, Gregory, for the introduction. So hi, everyone. I'm Neta, and I'm going to talk with you today about infinite counterexamples in deductive verification, why you should care about them, and how you can find them even though they're infinite. So first, the setting of deductive verification, and specifically SMT-based deductive verification. We have a system. We want to verify that it satisfies some properties. We add annotations to the system, like invariant, and we then use these to derive verification conditions, which are logical formulas that are satisfiable if and only if the system is incorrect. And specifically, we're interested in the case where we use uninterpreted first-order logic to express those verification conditions. We then hand these logical formulas to an SMT solver, and there are basically three outcomes. The formula can be finitely satisfiable, and then the solver will give us a finite counter model that shows an incorrect behavior of the system. The formula can be unsatisfiable, and then we'll get a proof that the system is verified. And the formula can be infinitely satisfiable, and then we have a problem. The solver will get stuck and will give no feedback to the user. And I want to stress that the key issue here is that the user does not know which of these cases their formula is in. So they can just keep waiting, hoping that the formula will get verified or that they'll get a finite counter model, but it will just never, the solver would never return. Okay, so in this regard, our work is comprised of three contributions. First, we present a finite representation of infinite models, which enables simple model checking. We present an efficient search procedure that allows us to find a satisfying infinite model for a given formula. And we have a decidability result that identifies a new fragment of first-order logic where satisfiability is decidable. And somewhat unusually, the decidability result also applies for formulas that only have infinite models. So some of you might be sitting in the audience and thinking, well, why do I care about infinite models? We're in computer science. Aren't we always interested in finite objects? And my answer is, well, we are, but when we abstract our problem in first-order logic, infinite models, though spurious, will invariably appear. And we specifically draw examples from two domains, distributed protocols, where we have rounds which are natural numbers, but we abstract them, and linked lists where we have the nodes in the heap as abstracted. Okay, so let's see this with an example. I'm going to use a simplified verification condition from Paxos. Paxos is a widely used and widely researched distributed consensus protocol. And I'm going to use a simplified VC from its correctness proof. So in this VC, we have two sorts, rounds and values. And as I said, we think of the rounds as natural numbers, but we abstract them with a total order. So we say that the order is anti-reflexive, that it's transitive, and that it's total or linear. Then we have this proposal mechanism, which have this invariant that for any round R and value V, if V is proposed in R, then either V is safe, or there's a previous round R prime where V was already proposed. This predicate safe V in Paxos, it's a complicated condition that ensures consensus, but for us, for this simplified example, it's enough to think of it as there can only be one safe value. And lastly, we want to see if the system can be buggy. So can there be two different values that were both proposed? And we take the conjunction of all of these formulas and we give it to a solver to see if it can verify the system. So we try to verify it, we give it to a solver, and we wait, and we wait, and we wait, and existing tools, existing SMC solvers can't verify the problem. Yeah, they just get stuck, they leave the user with no feedback. So is this just bad luck due to the quantifier alternation in the formula? It's a complicated formula. Maybe if we wait a little longer, we'll get a proof or a finite counter model. No. This formula only has infinite counterexamples. Okay, so how does this infinite counterexample look like? So we have two values, the safe V1 and the unsafe V2. we have infinitely many rounds going from left to right, from the smallest R1 to the largest R2.
I'm unmuted.
And we can think of the
wait,
binary
there's something
proposal
wrong with the
relation
audio?
as edges in this element graph. So V1 was proposed in R1, and V2 was proposed in R2, and also in all of the
Is this
other
the right
dark
channel
rounds.
for the
Yeah, and recalling the proposal mechanism that we had, we can see that the
presenter? I think
unsafe
I'll present
value
in 15
V2
minutes.
has an infinite chain of rounds in which it was proposed. And we can see that for every round there's a witness smaller round where V was already proposed, and this chain of witnesses is infinitely decreasing but never reaches R1. Okay, and solvers can't find this model, but because it exists, they cannot find a proof that the system is verified, and they just leave the user again with no feedback. Okay, so first, how do we represent this infinite model in a finite way? So looking at the model, we can see there's a clear repeating pattern here. Yeah, all of these dark rounds interact identically with the rest of the model. We can think of them as numbered with non-positive integers, going from 0 down to -1, -2, and so forth. And our key idea is that we can group them and describe the behavior of all these infinite elements in a symbolic, finite way. Okay, this leads us to finite symbolic representation of this model. So what do we have in this symbolic model? So it's comprised of 4 parts. We have the symbolic domain, which replaces explicit elements in the model with symbolic nodes. And we have 2 types of nodes: regular nodes, which are R1, V1, and V2, and they represent a single element. And we have summary nodes, which here is the dark node, which represent infinitely many elements. We use bound formulas to specify which subset of the integers are inside this summary node. So this summary node summarizes infinitely many elements specified by this I is less than or equal to 0. We then can define functions using function terms. So the witness function takes an element from the summary node to another element in the summary node by taking I to I minus 1. And we have relation formulas that specify how relation works. So we can see that for any 2 elements in the summary node, they are in order according to the abstracted order when their values are in order. And we can see that for R1, it's less than all of the rounds in this summary node. And all of the symbolic parts of the model are defined using the language of linear integer arithmetic, or LIA. And I wanna stress that this is not an abstraction. This is a finite representation of the exact infinite model we saw before. Okay, this is just a shortened way to present the same model that we had before. Okay. And this definition of symbolic models allows us to check satisfaction of FOL formulas. So given a formula phi and a symbolic model M, we construct a pure LIA formula, phi LIA M, such that the LIA formula is valid if and only if the model satisfies phi. Great. So next, okay, we can check if a specific model satisfies a formula, but can we find a satisfying model for a given formula? So of course we could just enumerate all symbolic models, but this is infeasible. And instead we narrow down the search space using the notion of a template that defines a more restricted search space. And how do we restrict it? We restrict ourselves to some symbolic domains, so some sets of regular and summary nodes, sets of possible bound formulas, sets of possible function terms, and set of possible relation formulas. And these combined induce a set of candidate symbolic models, but again, checking every symbolic model explicitly would be impractical, and in fact impossible if we have infinite sets. For example, all of the I is less than k for any k integer bound formula. So what do we do instead? We obtain a symbolic squared search procedure, which is a symbolic encoding for searching for symbolic models. So given a formula phi and a template t, we construct a pure LIA formula phi LIA t, such that if there exists an assignment v that satisfies the LIA formula, then there is an induced model mv in the template T that satisfies phi. Great. So the next question is, okay, so what's the template? How do we find the correct template to use? So which formulas do we need? Which terms do we need to consider? Which symbolic domains? And maybe most importantly, are we guaranteed to have a satisfying symbolic model? And the answer is yes, but only in some cases. So this leads us to our decidability result. So we identified a new fragment of first-order logic called OSC, ordered self-cycle, and the simplified Paxos VC that I showed you is in OSC. And OSC extends the decidable EPR fragment, the effectively propositional fragment of FOL, and where EPR restricts quantifier alternation to ensure finite models, OSC relaxes it a bit, and some formulas in OSC only have infinite models. So to understand the restrictions of EPR, we look at the quantifier alternation graph, which is a graph where we have for each sort a vertex, and we have directed edges for any for all exists quantifier alternation. So for this alternation, for all value exists round, we have this directed edge, and for this for all round exists round, we have this self loop. And EPR disallows any loops in the graph, so no loop is allowed. And in OSC, we relax it and allow one vertex in the graph to have self loops or self cycles. And the precise definition of OSC includes a bit more details, and you can find it in the paper. But the important property of OSC is that every satisfiable formula in OSC has a symbolic model, and further, it has a small symbolic model property, which bounds the size of the symbolic domains we need to look for, and fixes sets of possible relation formulas, bound formulas, and function terms we need to consider. And specifically, the symbolic model that we just saw falls exactly into these small model property models we need to check. Great. Next, so to evaluate the applicability of symbolic models, we developed a tool called FAST, which stands for Find and Evaluate Symbolic Structures via Templates. And FAST translates formula into symbolic search query, so into a LIA query, and hands it off to an off-the-shelf SMT solver, a CVC5. And if the formula is satisfiable, FAST will construct and present to the user the infinite model that satisfies it. And we evaluate FAST with examples from existing work, so existing examples of distributed protocols, like I mentioned, Paxos and other variants of Paxos, and also examples from linked lists, so properties of a sorted list, properties of list segments, and stuff like that. Okay, and so this is our evaluation. We have 21 examples. We can see that for the linked list examples, which are fairly simpler, there's only one sort, FAST finds an infinite model in less than 1 second. And for the distributed protocol examples, which are a bit more complex and involve more sorts and more relations and more functions, it takes more time, but still the slowest is just over 2 minutes, and the average is well below 1 minute. That's it. So to conclude, we developed the formalism of symbolic models and their model checking, and we use LIA as the underlying language to describe the symbolic parts of the symbolic models. We introduced templates as an efficient way to search potentially infinite space of infinite models. And we have a decidability result of the new fragment OSC, which is a superset of EPR. We have our tool here in the QR code. You can use it and see how it finds infinite models. And some notes on future work. So we looked at 2 domains, distributed protocols and linked lists, but this could be applicable to other domains. And maybe for other domains, we would need other underlying theories. So instead of LIA, maybe some other decidable theory. And also we have an example in the paper of formulas that have larger infinite models. So infinite models that would require symbolic models with infinitely many summary nodes. And we also discuss how this could be also handled in some way. And that's it. Thank you so much for listening. And I'm happy to take questions.
Are there any questions for Neta?
So the Thank you for the talk. The particular infinite model that you mentioned, it has a property that it has click width 2.
It has what?
There's click width is a number that you can associate to graphs, and this one I think has 2, and it is decidable. You can search through all possibly infinite models of click width 2. It's connected to tree width. So I was curious if this kind of approach of using these graph parameters is connected to the work that you're doing.
So I'm not familiar with the clickwood, but I think when we define a template, we're in some sense restricting the graph of the symbolic models we're looking at, and maybe it is connected this way. So when we define a template, we say this is like the symbolic domain. So this, in some way, defines the kinds of graphs you will get in the symbolic model.
So this could be useful because there's a large literature on this topic with a lot of important results. So
Okay, thanks.
Hi.
Is there another?
Can I ask my question or? Oh, hi. Just a quick question. So I was just wondering if the searching for these infinite counter models is at all related to some work about synthesizing recursive programs, like whether you could think of this structure as a kind of like recursive program, and whether existing work in program synthesis that synthesizes these recursive programs could be used in this setting, or whether you could, some of the techniques you use could actually work in that setting.
Yeah, it's hard for me to say. I'm not that familiar with the synthesis of recursive programs. I mean, I see the connection in that the summary node is some kind of a recursive call to itself, but it's hard for me to say something more than that.
One more over here.
Okay, so I just want to, nice talk. I just want to ask about the benchmarks. I guess what you're doing here is you have annotations for the invariants, right? I just want to, I think this is, so it's not like you're actually finding the invariants, no? Like for the...
No, we have all the invariants already. We try to verify them, but you can't verify them. There's a bug in the system. The bug is that there's an infinite models that the modeling does not take into account.
So like none of this can be done with Aviv, for example, or
with
Aviv, or
no.
the EPR only, yeah.
You could reformulate those examples in EPR, and then obviously you'd have finite models, and you could use Ivy, but we took examples that this was like the natural way to formalize them in already existing work.
I see. Yeah, thank you. Sorry.
We can do one more quick question up there.
Hi, I'm probably just being really stupid, but the axiomatization you gave at the start for your Paxos example, couldn't you just use the inbuilt support for natural numbers?
Yeah, so this is a good question. So we could use the natural numbers or integers instead, but then we would have first order logic with quantifiers and theories, which could be more difficult, could pose more challenges to solvers, and a lot of existing work are working with only using first order logic, uninterpreted first order logic, without theories, to make this problem of using quantifiers and theories together just to avoid this problem, if that makes sense to you.
It does, but the whole point of using an SMT solver is to use the theories.
So I use the term SMT also for the part that uses, like, can do quantifier instantiation and solve problems with quantifiers. Yeah.
Okay. We'll take the rest of it offline. Thank you so much.
Thank you.